Hello everyone and welcome to another interesting physics class on dimensional analysis. Today I'm going to show you how to derive Stokes formula using dimensional analysis. Without further ado, let's dive right into it. We have an interesting question here that reads, Stokes formula gives an expression for the viscous force acting on a small sphere moving through a homogeneous viscous fluid. The viscous force F acting on the sphere depends on the viscosity of the fluid, which is known as eta, the radius of the sphere, and the velocity of the sphere. Derive Stokes formula using dimensional analysis. The first thing that we have to do always is to extract the variables given in the question. We can see that we have that force, which is the F, depends. So we use this proportionality sign. It depends on, number one, the viscosity, which is known as eta. Secondly, it also depends on the radius, which is r. And lastly, it depends on the velocity of the sphere, which is v. Okay, having listed our given variables or parameters in the question, the next thing that we're going to do is to raise the right-hand side, okay, to powers of our choice. But they must be alphabets or they must be variables, because this type of problem would always lead you to simultaneous equations. So in case you do not know how to solve simultaneous equations with 2 and 3 variables, I would advise you go through my channel. You'll find those videos and they're going to help you out. So we say F is proportional to, this is eta, and we're going to choose A, okay? And for the radius, we use B. And lastly, for the velocity, we use C. Okay, now why are we doing this? Well, since they said that we should derive Stokes formula using dimensional analysis, we have to raise the right-hand side to powers and then solve for those variables, right? For example, here we have A, B, and C. If we solve for A, B, and C, the nature of these solutions will tell us about the outlook or the appearance of the formula. I'm going to explain it when we finally find the values of A, B, and C to know how your formula should look like and how it depends on the nature of the values. All right, now let's continue. Having raised them, the right-hand side to the powers of our choice. Remember, we're using variables here. We're not using numbers. We're just using variables. The next thing that we're going to do, or the next thing that you should do, is to remove the proportionality sign. And how do we do that? We say F is equal to, you introduce an equality sign and a K, okay? The equality sign and the K eliminates the proportionality sign. Now you can now bring back the right-hand side, which is eta raised to the power of A, the radius raised to the power of B, and then the velocity raised to the power of C. This K is dimensionless. It's a dimensionless constant in the sense that it does not have any dimension. So what do? We have to remove it from there because it does not have any dimension. And when we take it away, we are not going to be left with F is equal to viscosity, which is eta raised to the power of A, the radius raised to the power of B, and the velocity raised to the power of C. All right, now we've gotten to a point where we can now determine the dimensions of the variables in this equation, right? Now, if you look at the left-hand side, you will see that this is force. This one on the right-hand side is viscosity. We have our radius and our velocity. Now, the question right now is, how do we determine the dimensions of these variables? How do we do that? There are two ways that you can determine the dimension of any given variable. Step one, or the first method, is to know their units or its units. Once you know the units, you can derive the dimensions from those units. For example, velocity is measured in meters per second. Meters per second. We know that meter is a unit of length, and the dimension for L, or length, okay, is L. We have what we call the MLT system. This is mass, length, and time. This M here represents the dimension for mass, the L is the dimension for length, and then T is the dimension for time. So here we have the meter, and we know that the meter is the SI unit for length. Okay, then what is the dimension for length? We say L. And then this is over. This second is the SI unit for time. And what is the dimension for time? It is T. Therefore, we can equally derive the dimension of any quantity from its unit. It is practically possible. Now, the second method is to use the formula. So with the formula, you can also derive the dimension for whatever that you want. For example, force. We know that force is equal to mass times acceleration, right? Force is equal to ma. Now, what is the dimension for mass? The dimension for mass is just m, okay? Now, for acceleration is given as a rate of change of velocity with respect to time. The rate of change of velocity with respect to time. So we can now say, let me do it this way, acceleration is equal to change in velocity with respect to time. So this is delta V over delta T. Velocity, acceleration is the rate of change of velocity with respect to time. But the question right here is that we don't know the dimension for velocity, but we know that velocity, V, is giving us the rate of change of displacement, okay, change in x over change in time. Okay, so with this right now, the dimension x is measured in meters, right? Because it's displacement, and displacement is measured in meters. Now, meter is the SI unit for length. And what is the dimension for length? We just say L. And this is over. For the T, T is measured in seconds. And what is the dimension for time? It's just a T. Now, what we have to do right now is to take it away from the denominator by taking it upwards, okay? Now, if you take it upwards, this power down here is a power of 1, is a power of positive 1. When you take it upwards, it now becomes LT minus 1. Remember that down here at the denominator, we have something like L over T, right? And this T here is to the power of 1. That is the power of positive 1. But when you take it upwards, it now becomes LT minus 1. Therefore, the dimension for velocity, V, is equal to LT minus 1. Now, remember that we're looking for the dimension for acceleration. And that means that whenever we see velocity, we put LT minus 1. Okay. Now, let's continue. Here we have that acceleration is equal to, remember here we have delta V, and the dimension for velocity is LT minus 1, and this is over. Down here we have T, right? And this is time. Time is measured in seconds, and the dimension for time is known to be T. Therefore, we also apply the same technique by moving the T from the denominator. We take it upwards. It has a positive power of 1 down here. When you take it upwards, it now becomes LT minus 1, and then T minus 1. This T minus 1 that we have here, the first one was originally there before we now took this upwards, and it got attached to this. Now, we now have to apply what we call a multiplication law of indices that says if you have two like bases or two or more bases that are the same and they are multiplying, what do? You have to add their powers. For example, let's suppose you have a squared times a to the power of 3. Since a and a are like bases, we simply add their powers and we are going to obtain a squared plus 3. And this is equal to a to the power of 5. So we also employ the same method in this case by adding their powers, you can see that this t and this t are the same and they are multiplying here, so you can add their powers. And hence, we're now going to have that acceleration is equal to lt, then -1 plus -1 gives you -2. Therefore, the dimension for acceleration is lt to the power -2. Okay, now we can go back now. Remember that we're trying to determine the dimension for force, right? Now we can now go back and substitute. Since we already have the mass, which is m, we now have acceleration, we can substitute and see what we shall obtain. Hence, we have that the dimension for force is equal to ma, and for the mass, we determine that to be m, and then since the a multiplies the m, it now becomes the dimension for a gives us lt minus 2. So the dimension for force is mlt minus 2. We keep this aside. Correct. Now the next one that we have to find its dimension is radius. Radius is simply length because it's measured in meters, right? And the dimension for length is simply L. So the dimension for radius is L. There are no two ways about that. The next one is velocity. I'm going to do the viscosity as the last one to save time. So velocity is defined as the rate of change of displacement with respect to time. If you look at this right here, we've already determined the dimension for velocity, which is lt minus 1. Okay, so this is it here. Velocity is equal to the rate of change of displacement with respect to time. And after simplifying, we got the dimension for velocity to be lt minus 1. So we simply write it down here, lt minus 1. Okay, lt minus 1. This is the dimension for velocity. Now the last one is very tricky, and that is viscosity. What is the dimension for viscosity? Remember I said that you can or we can determine the dimension of any quantity using either the units or the formula. Now, you don't need to know the units of viscosity in order to be able to determine its dimension, but you can know its formula. And the formula for viscosity is force over area times velocity gradient. Okay, so force over area multiplied by velocity gradient, that gives you the dimension for viscosity. All right, so let's see how we can work this out. Now we have that the dimension for viscosity is equal to, we've already found the dimension for force, right? And we have it here as mlt minus 2. So whenever we see force, we replace it with its dimension to be mlt minus 2. And this is over, area is measured in meter squared, right? Area is length times length. So this is now going to be, since the unit for area is meter squared, okay, or area is measured in meter squared, we know that meter is the unit for length, and the dimension for length is just L. So we now say this is L squared, and this is multiplying velocity gradient. Now, what is velocity gradient? Velocity gradient is simply the rate of change of velocity with respect to distance, okay? The rate of change of velocity with respect to distance. So this can be written as dv over dx, okay? Now, let's do this step by step so that we'll not make any mistakes. We want to determine correctly the dimension of this eta or viscosity. So we can now write viscosity is equal to, we still have our mlt minus 2 on top, and this is over L squared, then multiplied by. So remember that this one on top here refers to the rate of change of velocity, and then the dimension for velocity is lt minus 1, and this is over, this is change in x or change in distance, the rate of change of the rate of change of velocity with respect to distance, and distance is measured in meters. Okay, and then since it is also length, distance is also length, the SI unit for distance is meters, and the dimension for length is just L. So this now becomes LT minus 1 over L. Let's now simplify. So here we have M LT minus 2. Then this is over L squared multiplied by. So I'm also going to apply the same method by taking the L to the top. Remember, it's down here. So we now have L, okay? When I take it to the top, it now becomes L, then times L. Remember, it's a power of positive 1 here, right? But if it goes upwards, it now becomes minus 1. And then we have the T to be T to the power negative 1. Okay, it's not anything complicated. I just took it away from the denominator upwards. Remember I said, if it has the power of 1 down here, if it goes up, it becomes a minus 1. If it has the power of negative 1 down here, when it goes up, it becomes a negative 2, and so forth. That is how it works. Now let's clean this up. We have that viscosity is equal to mLT minus 2 over, and here we have L squared. Okay, so this right here, this is L, please, it's not a 2. Here we have two like bases, L and L. This one is to the power of positive 1, and this is to the power of negative 1. So we cannot add their powers. Now, when you add the powers, what are we going to obtain? 1 minus 1 gives us a 0, or 1 plus negative 1 gives us L to the power of 0. Hence, that one goes away, and we're now left with, or we can just add them to show you how it works. Hence, we now have L to the power of 0, and then T to the power of minus 1. Okay, now let's clean this up. We have M L T minus 2 over, here we have an L squared, okay? And then we know that any number raised to the power of 0, apart from 0, is 1. So this number here is raised to the power of 0, or the letter L is raised to the power of 0. And if you raise the letter L to the power of 0, it simply means it's a 1. 1 times T to the power of negative 1 gives you T to the power of negative 1. Now we are almost done. Let's see. So this is viscosity is equal to, I'm going to move everything down here to the top, okay? Let's move them to the top. We have our M. Please write them in the form of MLT. The M comes first, followed by the L, and then next you have your T. So this is now going to be ML, okay? Now when I move this L to the power of positive 2 to the top, it now becomes L minus 2. And the next one here is this T. This T is to the power of negative 1. When I take it upwards, it now becomes a positive 1. And we also have this one up here. So we have T minus 2. Now let's clean this up to see what we shall obtain. The dimension for viscosity is equal to M. Okay, so we said if we have two like bases, you have to add their powers. This one is to the power of positive 1. Then 1 plus minus 2 gives you minus 1. Hence, you have ML minus 1. And then your T, here we have a positive 1, right? Now, 1 plus minus 2 gives you minus 1. So, we now have ML minus 1, T minus 1. This is how to find the dimension for viscosity. So, you can decide to memorize it or understand how it works. Whichever one is still okay. Okay, having found the respective dimensions, we can now start solving the problem. So here we have that the force is equal to viscosity, the radius, and then the velocity. So wherever I see F, I'm going to put its dimension. The dimension for force is giving us M L T minus 2. Okay? And then this is equal to the dimension for viscosity. We've already determined that to be ml negative 1 t negative 1. Hence, we now have, this is to the power of a, b, and c. So we have m l minus 1, and then t minus 1. Okay? You can close it and raise e to the power of a. The next one there is a radius, and the dimension for radius is just L, and this is raised to the power of b. And then finally, we have our velocity, and the dimension for velocity is giving us Lt minus 1, and this is raised to the power of c. Now, having substituted, the next thing that we're going to do right now is to distribute the powers, okay? So the a goes to the m, goes to the L, goes to the T. This is a minus 1, please. This is minus 1. Then the B goes to the L, the C goes to the L, the C also goes to the T minus 1. So let's do that. We have M, L, T minus 2. This is equal to, so this M now becomes M to the power of A. Remember that we're distributing, okay? Next we have L to the power of minus A. Here we have T to the power of minus A. Remember that this is minus 1. So minus 1 times A gives you minus A. Then here minus 1 again times A gives you minus A. And for the L, or for the B, we now have L to the power of B. And for this one right here, we have L to the power of C. And then minus 1 times C gives you T, okay, to the power of minus C, okay? So something like that. All right. So having done this, what's the next thing that we are going to do? So the next thing to do right here is that we are now going to rearrange them. So we pick the M's first, then we pick the L, and then we can pick the T, okay? That's how to do it. We pick the M first, we pick the L, and then the T. Hence, we now have M, L, T minus 2 is equal to, let me rearrange them, M to the power of A. We only have one M, so we don't have to bother. Now, the next one here is our L, right? We have L to the power of minus A. We also have another L, which is L to the power of B, and one more L to be L to the power of C. And now let's go ahead and work on the T's. We have the first T to be to the power of minus A, and then the second T is to the power of minus C. Okay, so right now, what do we do at this point? So when we get here, we now have to add their powers since the bases are the same. So we add for the L and for the T. So let's do that. We have M, L, T minus 2 is equal to, here we have one M, just an M. We don't have to bother about adding it to something else. But this now becomes L to the power of minus A, then plus B, and plus C. Okay, if the bases are the same, you have to add their powers. And then for the T, we have minus A minus C. We've added these ones together. Like I said, don't forget, if the bases are the same, you have to add their powers. That's the rule. Now, at this point right now, we can now compare and we can now equate the powers. So we say equating their powers. Why are we equating the powers? Because we have like bases on both sides. If you have like bases in mathematics, for example, let's say you have 4x, or 4 raised to the power x is equal to 16. You are being asked, what number will I raise, or do I need that when I raise that, when I raise this 4 to that number, okay, which we don't know, we get a 16. Okay, so that means that if you put a 2 here, for example, 4 raised to the power 2 will give you a 16. But you cannot just guess the number. What you have to do is to solve it, and then that's going to be by rewriting this 16 to something else. So 16 can be written as 4 raised to the power of 2, okay? Because 4 raised to the power of 2 is equal to 16. Now, when the bases are on both sides are the same, you can simply cancel them out and equate their powers, okay? You can now equate their powers. So that's the same thing that we're going to do right now. So we can simply see that what we have on the left equals what we have on the right, okay? So we can now equate their powers. Now look at the m and the m, okay? When you equate their powers, because remember that this m and m are the same, you can now say that the power of m on the right, a, is equal to the power of m on the left, which is 1. Okay, so a is equal to 1. Now let's do for the L. For the L, we have minus a plus b plus c is equal to the power of L on the other side, which is a 1. So this gives us a 1. And finally, for the t, the powers of t on the right is minus a minus c. We say minus a minus c, this is equal to what? Minus 2. So you have to compare their powers. Please don't mix things up. Don't give the powers of L to T and don't give the powers of M to L. It's not going to work that way. It must be M for M, L for L, and T for T. Hence, we now have a minus C is equal to minus 2. This is our 1, this is our equation 2, and this is our equation 3. Now, we can now solve them simultaneously to determine their respective values. We already have our A, okay? So we don't have to do anything too technical. We can't use elimination in this case because the equations are not perfectly aligned. You can see that equation 1 only has an A. Equation 2 has A, B, and C. Equation 3 has A and C only. So we can't use elimination method. It's not going to work. So we have to use substitution method. So I'm going to say solving for C. I'm going to solve for C, okay, using equation 3. So since I have my A already, I can use this A to find my C. We have minus A minus C is equal to minus 2. What's our A? Our A is 1, right? Correct. So we now have minus A, since our A is 1, then minus C is equal to minus 2. Then 1 times negative times 1 gives you a minus 1. Then minus C is equal to minus 2. Okay. Now let me try to rearrange it this very way. I'm going to take the C to the other side and the negative 2 to the other side. Hence, we now have minus 1. Then if this negative 2 crosses the equality sign, it becomes a plus 2. And this is equal to, when the negative C goes over, it becomes a C. Okay? So now, this is now going to be written as minus 1 plus 2 is going to give us a 1. So 1 is equal to C. We can write it properly that C is equal to 1. So this is the proper way of writing it. Okay, we've determined the value of C. Now, since we found the value of C, we can now go ahead to look for the value of B using equation 2. Correct. So we solving for B using equation 2. Our equation 2 here is minus A plus B plus C is equal to 1. So we've determined our A to be 1, right? Here we have minus 1, then plus B. Since our C is a 1, we put it there. We have plus 1. This is equal to 1. So here we have minus times 1 gives us minus 1. And this is plus B plus 1 is equal to 1. Correct. So minus 1 plus 1 gives us a 0. Hence, B is equal to 1. Okay, we have found the values of A, B, and C. We found that A is equal to 1, B is equal to 1, and then C is also equal to 1. So having found these very values of these powers, okay, remember that the powers are A, B, and C. Now having found these answers, the next thing to do right here is to bring back the expression that we wrote that the force is proportional to the viscosity to the power of A, and the next one is the radius to the power of B, and then the velocity to the power of C. So wherever we see A, we put a 1. Wherever we see B, we put a 1, and wherever we see C, we also put a 1. So this now becomes F is proportional to viscosity to the power of 1, the radius to the power of 1, and then the velocity to the power of 1. Okay, so since the values are just the same, like 1, 1, 1, it means that the equation is going to be something like this. It's not going to be in a square root form. It's not going to be in a fraction form. It's just going to be in a linear form. Okay, so we can now say, let's now remove this sign here and put a K. So we have the force is equal to K, and then we have our viscosity multiplied by the radius, and then multiplied by the velocity. So this is Stokes formula. Okay, this is Stokes formula. Now we don't know what the K is, but the formula itself, the K is 6 pi, but this one is the most acceptable solution since we just assume that we don't know what this K is, but we know that this K here is dimensionless. So wherever we take the place of K is always going to be dimensionless, but this is Stokes formula. So that's how it is. Now, in addition, for example, let's assume we solved and then we got that A is equal to, let's say, 1 over 2, and then B is equal to, let's say, negative 1 over 2, okay? And then let's say again that C is equal to 1 over 2. So what this means is that the formula will now be in square root form. You now have something like F is equal to K, then multiply by the square root, okay, of viscosity multiplied by, what do you call it? Multiplied by the B, which is the radius, and then over, okay? So the radius here is negative, so it is going to go down, okay? So now it's multiplied by the velocity over the radius. Why? Because using the fractional exponent law, if you have the square root of A, the square root of A can be written as A to the power of 1 over 2. So for example, once you get half, it means that your formula will be in square root form, okay? And if you have a negative number, it means that it's going down, okay? If you have a positive number, it's not going to go down, it's going to be at the top, something like that. So this is how to derive Stokes formula using dimensional analysis. And I believe you understood this video. If you have any questions, comments, or concerns, you can reach out to me in the comment section and I'll be right there waiting for you. Thank you and see you in the next video.